Okay, let's dive right in. You know that feeling when you open up Netflix, hoping for some sci-fi magic, or maybe Spotify, craving that perfect jazz playlist?
Oh, yeah, definitely.
But it's like the algorithm just threw a dart at a board. It treats you like user hashtag 78932. No clue about your passions.
Yeah, like you're just a number.
It's if they have zero understanding of what makes you you.
That's a spot-on way to put it, actually. Under the hood of many of the recommendation systems we use daily, that's pretty much what's happening.
Really, just random numbers.
Mostly, yeah. Users and items are represented by these random, unique IDs, just numbers, you know? They're devoid of any inherent meaning about what you like or what something is.
Exactly. And this creates a real challenge for the AIs trying to figure out what you might want next.
For sure.
It's like trying to sort a mountain of Legos without any instructions or knowing what the final picture is supposed to be. The model has to learn every single connection from scratch.
Which leads to some familiar frustrations, right? Think about signing up for a new service. Those initial recommendations often feel, well, generic.
Totally. The cold start problem.
That's the one. Similarly, surfacing those really specific niche items that only a small group of people are interested in, that's another significant hurdle.
The stuff hidden way down the list.
Right. And even new items that haven't had a chance to gather many interactions yet, they struggle too.
So this begs the question, what if these IDs actually told a story?
Yeah.
What if, instead of user hashtag 50281, the system understood loves vintage jazz, lives in Vancouver, and item hashtag 927 was tagged as epic space opera set in the far future? It feels like that would give the AI a massive leg up in understanding, wouldn't it?
Precisely. And that's the core idea behind semantic IDs. It's a seemingly small change adding meaning to an identifier, but the implications are, well, profound.
Okay, so it's not just a number anymore.
Not at all. Research, like that 2023 paper on semantic IDs, demonstrates how this approach allows models to learn more quickly and make better recommendations, especially for things they haven't encountered much before.
Right, better generalization.
Exactly. And this deeper understanding also opens the door for more serendipitous recommendations. Because the system understands, loves vintage jazz, lives in Vancouver, it might suggest a related genre or maybe a Canadian artist you haven't explicitly engaged with, but it aligns with your semantic profile.
That makes sense. Finding things you didn't even know you were looking for.
Yeah, that kind of discovery.
So, on this deep dive, our goal is to unravel how these semantic IDs work. How do you actually inject this meaning into what were once just arbitrary numbers?
Good question.
And how is this seemingly simple concept transforming the massive AI engines that power the recommendations we see every day?
Well, let's begin by understanding why those traditional random IDs present such a fundamental challenge. As we've kind of touched on, these systems assign an arbitrary, unique identifier to every user and every item.
Whether it's a video, a product, whatever.
Exactly. A video, a product, a podcast episode.
Right. It's like giving every single product in a massive warehouse a random barcode and then trying to figure out what someone might want to buy based solely on which random barcodes other people have scanned together.
It's a great analogy.
You wouldn't know if it's groceries, electronics, or gardening tools.
Exactly. These IDs carry no inherent information about the user's preferences, their background, or, any details about the item itself, its category, its themes, its creators. Nada.
And this lack of inherent meaning leads to some significant drawbacks.
Right, definitely.
Okay, lay out the main problems for us. What are the key downsides of relying on these random identifiers?
Well, first off, it places a huge memory burden on the model. It has to learn each individual user-item interaction as a completely isolated piece of information.
Like memorizing billions of unrelated facts.
Pretty much. There are no built-in connections or similarities it can leverage. Second, as we touched on, it makes generalization incredibly difficult.
The gold start thing again.
Yeah. If the model hasn't seen many interactions for a new user or a very specific niche item, it really struggles to make relevant suggestions. It's operating in the dark, essentially.
So it just defaults to popular stuff.
Often, yes, or just gives up. And third, it's incredibly data inefficient. You need massive amounts of interaction data just to train effective embedding.
Embeddings. Those are like the coordinates in that meaning space, right?
Exactly. Think of them as numerical vectors in a high-dimensional space.
Yeah.
The closer two items or users are in this space, the more semantically similar they are meant to be.
Okay.
But without inherent meaning in the IDs, the model has to learn this entire embedding space from scratch, based solely on interactions, which takes a ton of data.
So in essence, Using random IDs creates this vast, unstructured digital landscape where the model has to essentially memorize every single interaction. It's like trying to navigate a sprawling city without a map or any street names.
Precisely. Now let's contrast that with the concept of semantic IDs. This approach fundamentally shifts the paradigm by making meaning the foundation.
Making meaning the default.
Yeah, you could say that. Instead of these arbitrary labels, we're embedding real-world information directly into the identifiers themselves.
Okay, give us that before and after comparison again, because that really crystallizes the idea for me.
Sure. So a traditional system might see user hashtag 50281 and item hashtag 927, just numbers.
Right.
With semantic IDs, that could be transformed into something like user, interested in 1960s bebop jazz, based in Vancouver, Canada, and item, science fiction novel, theme, interstellar travel, author, Ursula K. Le Guin.
Wow, okay, that's a lot more informative.
You can immediately grasp the wealth of information now associated with those identifiers, right?
Yeah, it's a fundamental shift in how the system perceives users and items.
Yeah.
So where does this extra information come from? How are these semantic IDs actually created?
It originates from what's known as side information.
Side information.
Yeah. For users, this could include their demographic data, maybe their stated preferences if they provide them, or their historical behavior, the types of content they've engaged with previously.
What they've watched or listened to.
Exactly. For items, it's their metadata, the genre of a film, the artist of a song, the category of a product, textual descriptions, things like that.
And if it's text, like a movie description.
Right. For text-based information like movie descriptions or user reviews, we need ways to extract this meaning. Techniques like n-gram models.
N-grams.
Yeah, they look at short sequences of characters. Or subword piece models, which learn common, meaningful subunits of words. They help us create these semantic representations.
Okay, like breaking words down.
Sort of. For example, with n-grams, YouTube might become you, out, you2, tub, yube, little overlapping bits.
Ah, I see.
And subword piece models might break playing into play, ing. These create compact vocabularies for semantic representation without needing massive dictionaries.
Gotcha. So instead of the model starting with a blank slate, just seeing a string of random numbers, it now begins with this inherent understanding of the users and the items.
That's the goal.
It's like giving it a semantic compass right from the outset.
Exactly, a head start. And this integrates into the recommendation process quite naturally. You have your side information feeding into a semantic ID generator.
Okay.
This generator produces the semantic IDs, which are then used to create semantic embeddings, those numerical representations we discussed.
The coordinates in meaning space.
Right. These embeddings then feed into the ranking model, which ultimately generates the recommendations you see. It's about building richer, more informative representations from the very beginning to enhance generalization.
Okay, conceptually this is clear. It makes a lot of sense. But you mentioned the challenge of scaling this to billions of users and items, especially for platforms like YouTube. That sounds tricky.
It is.
How do you handle that immense scale with these meaningful IDs without the system becoming totally bogged down?
That's a critical consideration, absolutely. Storing vast, information-rich vectors for every single user and every single item would indeed be computationally expensive and could slow things down significantly.
Yeah, I can imagine.
That's where techniques like residual quantization, variational autoencoders, or RQVAE come into play.
Okay, RQVAE. Break that down a bit.
Sure. So to handle the scale, we need to compress this rich information. Think of a variational autoencoder, the VAE part, as a smart compression algorithm.
Like zipping a file.
Kind of, but way smarter. It tries to capture the most important essence of the user or item in a smaller package while still retaining the core meaning.
Okay, compress the essence. What about the RQ part, residual quantization?
Right. The residual quantization part is like iteratively fine-tuning that compressed package. It looks at the error, the difference between the original and the compressed version.
Residual.
Exactly. And it makes small corrections, quantizing that residual error to ensure we don't lose too much detail in the squeeze. It refines the compression.
So it's like compressing, checking what got lost, and then compressing that leftover bit too.
That's a pretty good way to think about it, yeah. It allows us to represent those rich semantic embeddings in a much more compact form as semantic IDs.
RQVAE sounds sophisticated. So it takes all that detailed semantic information, compresses it down into a manageable size, but tries to preserve as much of that original meaning as possible through this process of initial compression and then refinement.
Precisely. The process typically involves encoding the side information into a dense semantic vector. Then a first quantizer makes a coarse approximation of that vector.
Step one.
Then a second quantizer, and potentially even more, steps in to refine the error left by the first one, like we just discussed.
Fine-tuning.
Yep. The final output is a set of compact semantic IDs, like that example from the paper, maybe something like 1462, a short sequence of numbers.
So that sequence of numbers isn't random anymore. It represents a compressed but still meaningful summary of all that rich semantic information.
That's the key. It's compact but meaningful.
And the benefits are clear. You significantly reduce storage costs, you still retain a good degree of that semantic richness, and it enables much faster lookups when the system is actively serving recommendations.
Exactly. Faster, cheaper, and still smart. That figure in the paper really illustrates this recursive quantization process, showing how that initial detailed vector gets distilled down into those compact yet informative semantic IDs.
And this isn't just a theoretical idea, right? You
Yeah.
mentioned that YouTube is actually employing semantic IDs in their Watch Next system. How does that work in the real world?
Yes, absolutely. Within YouTube's massive recommendation infrastructure, semantic IDs have replaced those traditional random IDs in crucial stages.
Like where?
Like in candidate generation, that's identifying the initial set of videos a user might be interested in, and then also in the final ranking of those videos.
So if you're a new user on YouTube, or if there's a brand new video that hasn't gained many views yet, the system doesn't have to rely solely on past interaction data anymore.
That's a major advantage.
It can infer your potential interests or understand the content of the new video based on its semantic similarity to content it already understands.
Exactly. It can look at the semantic ID and say, ah, this new video seems semantically similar to other videos this user liked, or this new user's profile looks similar to other users who enjoyed this type of content.
That's huge for independent creators or smaller channels that might struggle to gain visibility in traditional systems.
That's precisely right. It helps level the playing field a bit for newer or niche content. And the beauty is that these semantic IDs could be integrated relatively seamlessly into YouTube's existing recommendation architecture.
So it wasn't a rip and replace everything kind of situation.
No, it seems more like a strategic replacement of those less informative identifiers with ones packed with meaning, adapting the existing pipelines.
And the outcomes of YouTube have been significant, right? What do they see?
Well, the reports indicate improved recommendations for those new or less popular items, definitely. Greater adaptability when a user's preferences evolve over time.
Because the ID reflects their interests more directly.
Plausibly, yes. And overall enhanced ranking quality, particularly for content the system hasn't seen much before.
The experimental results detailed in the research paper really highlight these advantages too, don't they?
They do. They found that semantic IDs consistently outperformed random hashed IDs. And this was especially evident in those challenging cold start scenarios we discussed earlier. Big improvements there.
What I found particularly interesting was that the paper also noted that simply using those dense content embeddings directly, the rich vectors before the RQVAE compression into semantic IDs, that actually performed worse than even the random hashed IDs. That seemed a bit surprising at first glance. Why would more information be worse?
That's a fascinating point, and it surprised the researchers too, I think. Their hypothesis revolves around how these large-scale ranking models are trained.
Okay.
They suggest that these models might heavily rely on the memorization capacity provided by those huge ID embedding tables associated with random IDs.
So the randomness and the huge table size actually help it memorize specific user item pairs.
That seems to be the idea, simply swapping them out with fixed dense vectors, even if they carry more semantic information theoretically, can disrupt this learned memorization pattern.
It breaks the model's habit.
Potentially, yes. And that can lead to poorer performance in certain setups. So it's not just about having the meaning, but also about how that meaning is structured and integrated into the existing system architecture. The quantization step seems key.
That makes sense. It's about fitting the meaning into the system's way of working. And the paper also explored different methods for generating those semantic IDs from text-based site information, right? You mentioned n-grams and SPM.
Yes, subword piece models, SPM. They looked at both.
And how did they compare?
They observed that both of these techniques led to substantial improvements in generalization compared to just using random hashing. Both worked much better.
Any difference between n-grams and SPM?
There were some nuances. The paper noted a slight advantage for n-gram models in smaller embedding table setups, But SPM models seem to scale better and offer slightly better generalization in larger setups, which is often the case in places like YouTube.
Interesting trade-offs. And the paper also provides specific metrics on the percentage improvement in things like CTR-AUC.
Right, click-through rate area under curve, a
Right.
standard metric.
Clearly demonstrating the lift achieved by semantic IDs compared to the random hashing baseline, especially when you consider users with or without history.
Yes, the quantitative results were quite compelling.
So bringing it all together, semantic IDs appear to be a really impactful advancement, a clever way to inject meaning. But as with any innovation, there must be considerations, right? Potential limitations or areas where further progress can be made.
Absolutely, nothing's perfect.
Like, how static are these IDs? If my tastes change dramatically, does my ID update?
That's one of the key limitations currently. Semantic IDs, in their present form, tend to be relatively static unless the underlying model is retrained, which can be resource-intensive.
So my ID might drift out of sync with me.
It could, yes. The meaning embedded in the IDs might become less accurate over time as user preferences or even item characteristics change. Your example of movie tastes shifting is spot on.
Okay, what else?
Well, there's the reliance on the quality of the site information, garbage in, garbage out, right? If the data used to generate these IDs is flawed, incomplete, or biased.
Then the semantic IDs won't be very good, or could even be harmful.
Exactly. And while residual quantization is effective for compression, there's always a potential for some loss of semantic nuance during that process. You're squeezing information.
Some fidelity might be lost.
Potentially. And finally, even with more compact IDs, managing the scalability of the entire system, including periodic retraining and updates at web scale, remains a significant engineering undertaking with associated computational costs. It's not free.
So what are some potential future directions or enhancements that researchers might investigate? Where does this go next?
The research community is actively exploring several promising avenues. One is the development of dynamic online updating mechanisms for semantic IDs.
So they could change in near real time.
That's the goal, allowing them to adapt to evolving user and item characteristics without requiring full model retraining every time. Another area is exploring self-supervised learning techniques.
Learning from the data itself.
Right. To extract features from raw data, which could reduce the dependence on manually engineered site information and potentially capture deeper patterns.
Making it less reliant on predefined metadata.
Exactly. And finally, ensuring fairness and mitigating potential biases in the generation of semantic IDs is a crucial area of ongoing research. We need to make sure these meaningful IDs don't accidentally reinforce harmful stereotypes.
That's incredibly important. This has been a truly insightful deep dive. It's remarkable how this seemingly subtle change, just embedding meaning into an ID, can have such a fundamental impact on how recommendation systems function.
It really is quite elegant, isn't it?
It represents a shift, like you said, from systems merely memorizing patterns to developing a more fundamental understanding of the content and the users.
Absolutely. Semantic IDs represent a significant step forward in building more intelligent, data-efficient, and ultimately more human-centric AI systems for recommendations. They bridge that gap between raw interaction data and a richer, more meaningful representation.
So for you, the listener, consider this. Where else in our digital world do we rely on seemingly arbitrary labels or identifiers? Could the principle of embedding meaning into those identifiers enhance understanding or efficiency in other domains beyond just recommendation systems? Think about areas where labels seem random but could carry richer information. It's definitely a fascinating concept to ponder. Thanks for joining us on this deep dive.